This is the video on neural summation. The action potential is an all or none process. So how does the brain know how intense a stimulus is? How can a light touch compare to slamming your finger in the car door when the signal from both is the same? The action potential starts when the membrane of the neuron depolarizes by about 15 millivolts or reaches threshold. This will trigger the voltage-gated sodium channels to open. Sodium will explosively move into the cell down both its concentration gradient and its electrical gradient. This depolarizes the membrane to about positive 40 millivolts. At this point, the sodium channels close and the voltage-dependent potassium channels open. With the cell now positive on the inside, potassium will move out of the cell, down both its concentration and electrical gradients. Potassium is a bit eager in doing this, ending up hyperpolarizing the cell below the typical resting potential. The potassium voltage-gated channels close, and the membrane returns to its normal resting potential. This happens the same way every time the cell reaches threshold. There are two ways the brain receives signals to let it know the car door just slammed on your finger. One is the number of neurons sending in signals. The other is how fast they come into the brain. When an injury or accident occurs, many neurons are triggered in response. This sends in a lot of information to the brain all at the same time. This large amount of incoming information lets the brain know the intensity of the stimulus. The more signals, the more intense. This is known as spatial summation. The other way the brain learns of intensity is by the timing of the signal. An intense signal will fire more rapidly than a light signal. Input coming in at several signals a second is interpreted as more intense than a signal coming in a few times per second. So, the receiving cell in the brain gets afferent signals from the body about pain, touch, heat, cold, pressure, and so on. This afferent signal looks like every other afferent signal. The arriving signal comes in at the same speed as every other signal. The speed of the action potential is determined by the size of the axon and whether it's myelinated. It hits the receiving neuron at the speed no matter what the intensity. It is how quickly the next action potential hits the receiving cell that determines the intensity of the stimulus. It is like listening to a telegraph. The dots and dashes are all the same tone. It is how fast they arrive and in what order that is the message, not the signal itself. Only the brain does not have dots and dashes. It only has the one signal, so it's even more complicated. This can be illustrated by looking at the muscle cells. When an action potential hits a muscle cell, it will produce a twitch. If another action potential hits the same cell before it relaxes to baseline, the twitch will become larger. As this continues, the strength of the muscle contraction will continue to build. Finally, the muscle will no longer be able to contract further, and you will reach what is called tetany, a fully contracted muscle cell. This is known as temporal summation. Muscle cells are innervated by only one axon, so they cannot receive input from another source, but brain cells can. The brain has both temporal and spatial summation to give it the gradation to determine the strength of a stimulus. It also works on the motor system, so it gives us the ability to gently pick up a kitten or expertly lift a 20-pound sack of dog food. This ends the video on neural summation.